Section 9.5 in Chapter 9 is called Properties of Polarity Marks. And this is sort of the last one of these where we're defining particulars of the transformer and the designations and so forth. And we'll look at a figure here, and as we're going through this and help make sense of it. But based on what we've talked about already and the way that this device works, and remembering that when we work with a transformer, we really only have access to 4 terminals, 2 on the primary side and 2 on the secondary side. So, all that we're going to talk about here in this section, it's not something that we can see or that we even need to see. But to understand how the transformer works, we need to understand it. Okay, again, this is back to figure 9.5, but again, this is what we're working with so far. We've discussed all the parts of this and what each one of these mean. In the last section we talked about these polarity marks. Okay, so again, knowing that a transformer is enclosed and we normally do not want to be inside of that transformer, we only want to access the terminals for the primary and secondary side. So there are some rules that we're going to just go through, and here's the basic rules that apply to these polarity marks. Okay, so the first rule says that a current entering a polarity mark terminal produces a magnemotive force that acts in a positive direction. Okay, so if the current is entering a particular polarity mark, then we're saying that by the sense that it's entering, that it's producing a flux in a clockwise direction. Okay, so that's what he's trying to show us with this. The magnemotive force acts in a positive direction, therefore there's a flux produced in a positive direction. He says the converse of that is that a current flowing out of a polarity mark terminal will produce MMF and a flux in a negative direction. Thus, the currents that respectively flow into and out of polarity mark terminals of 2 coils produce magnemotive forces that buck. Now, that is another one of these old electrical terms. Buck means to oppose. And you'll see later on in some of your other courses where, you're talking about a buck boost, depending, on the application, and when you talk about amplifiers and that sort of stuff. Okay, but again, if we say that the current comes in a polarity mark terminal, it forms, a positive flux that has a direction as such. Okay. And then if current were flowing out of a mark, say here, then think about there being another coil over here, it would produce a flux in the opposite direction, and they would be opposing each other, or the electrical term they call buck situation, where they're opposing. Okay, then the second rule that he says if one polarity mark terminal is momentarily positive, then the other polarity mark terminal is momentarily positive. Okay, like here and here. The rule enables us to relate the phasor voltage on the secondary side with the phasor voltage on the primary side. Okay, so let's see if I can make sense or help make sense of this for you. Okay, so what that would mean would be, that they would be in phase if I was connected here and here based on the polarity marks. And how do I represent that in a phasor diagram, well, here's voltage EDC, and that, double subscript means that the D is at the higher potential, the positive, and the C is at the lower potential, the negative. So EDC would be in phase with EAB, okay? And we see that phase relationship here, and the relative length of the phasors shows that EAB is a larger voltage than EDC. So we're inputting a larger voltage, getting a smaller voltage out, but they are in phase if we are connected in this manner, okay? So, I guess that would be the importance of the polarity mark and understanding these relationships, and what that would mean in terms of the flux. What that would mean in terms of the flux is, the flux produced on the primary side would be in this general direction, and then connected from here on the secondary side, that flux would also be in that direction if they were in phase. Here's a situation where, the connection is, where they're not bucking each other, but they're increasing each other. Okay. Now, work with that, see if you can make sense of it. Again, a lot of these relationships deal with the construction of the transformer. And at one level, it's not critical that, you get all of this in the sense that, say, hey, I completely understand that. But I want you to be able to understand, why you connect a certain way when you are interacting with transformers, that you understand that these polarity marks, if current is flowing in this one, right, it has a positive, and at the same time, if it is flowing into this one, it has a positive. And so those relationships are such that we can define these phasor voltages this way, okay? And, email me if it doesn't make sense. Hey, I'm not getting this. I've got some other things I can show you. Hopefully that would clarify that for you. All right, so from now on, we're actually going to connect a load to this transformer. We're going to see all the interesting things that happen, but we've sort of made our definitions now, and these defined relationships, and the way that this thing works is going to apply to whatever size transformer that we're working with, and it doesn't change in low power, high power, whatever.